We are rolling along. This is the second to last session here in track A, and we are talking about a blueprint for real-time data architecture. Now, before we begin, a few final notes. There's a chat window on the page you're in. You can post your questions there. You can interact with other attendees, and we will have a short session of Q&A after this main session is done. You may also tell us about any technical issues you might face, and we'll do our best to tackle them. Finally, make sure to check out the networking area where you can meet other attendees, other speakers, and continue the conversation that we'll start here today. Now, I'm excited to have two speakers with us today, and let me briefly introduce them. First, we have Frank McSherry, and he's a co-founder and chief scientist at Materialize, a SQL platform for processing and streaming data. Prior to Materialize, Frank was previously at Microsoft Research Silicon Valley, where he co-invented differential privacy and subsequently led the NAID project. He holds a PhD in computer science from the University of Washington. Alongside him, we have Arjun Narayan. He's also the co-founder and chief executive officer at Materialize, a SQL platform for processing and streaming data. Prior to Materialize, Arjun was an engineer at Cockroach Labs, where he worked on performance and distributed query execution in Cockroach DB. He holds a PhD in computer science from the University of Pennsylvania. With that being said, let's get started with today's session, and we'll see you soon for the Q&A.
My name is Arjun Narayan, and I'm from Materialize. I'm here today with my co-founder, Frank McSherry, and today we're going to talk to you about Materialize and its connection to streaming SQL. In particular, we're going to talk to you about standard SQL and its applicability to streaming. Now, before we start, I want to set up a little bit of common context. So a lot of you are probably familiar with standard transactional databases like Oracle or Postgres or MySQL. These are often called OLTP or online transaction processing databases. You can put a lot of business critical data in it, you can write to it, read from it, and in particular it will remember all of your data, and you can rely on it for a few fundamental properties. So you can rely on it not to lie to you, order all these transactions, especially deal with really high speed of transactions, low latency, high concurrency, things like that. Now, of course, in any business, including probably your own, just writing things down isn't your only use case, right? You have a lot of other analytics style uses for your data. In particular, these analytics queries are structured very differently from those very basic read and writes, transactional reads and writes. And if you pointed those queries at your OLTP database, that OLTP database is generally speaking not going to handle that kind of new workload very well. Now, of course, this sort of use case for your data is very valuable, so you can't just say no to this kind of query. Now, this isn't a new problem, so it's a fairly standard solution to use a second database specifically for these analytics use cases. Now, since you have two separate sort of kinds of things going on, there's an opportunity here. You can use two separate systems for these two separate use cases. And those two systems don't have to be identical. There's an opportunity for specialization, and by and large, that's how we get the OLAP system, or the online analytics processing system. This divergence into two different designs means, for instance, OLTP systems are generally row-based. We are optimized for getting reads and writes in and out the door as fast as possible, very efficiently. OLAP systems are generally columnar, which is they're optimized for grinding over very long columns of data and doing very efficient aggregations and things like that. Now, of course, there's this third component, this line in the middle, the ETL tether that's holding the whole system together. The extract, refers to getting the data out of the OLTP system. The T is transforming the data from one form to the other. And the L is loading it into the OLAP system. It's very helpful, keeps these concerns fairly separated, and both sides live happily ever after, right? No, well, not quite, right? So the main pain point with this separation is this fundamental limitation on data freshness that's available for analytics. This sort of system generally works well if analysts are querying yesterday's data, or better yet, they're querying even further back in history. But it doesn't quite work for use cases that require fresh data. The lag in the system from the left to the right side typically is measured in days, at best hours, and forget about milliseconds. Now, today we're going to talk to you about a third type of system, what we're calling an online view maintenance system, or an OLVM. We're going to argue that this is not just better for your existing set of analytics queries by making them faster, fresher, cheaper to maintain, but also enables a fundamentally new class of task. So what is this system? The main pivot is in changing the OLAP system from traditional pull-based architectures to a push-based architecture. Now, what I mean by pull and push is fundamentally any pull-based system sits around doing close to nothing until it's asked to perform a specific task by a query. OLTP systems and traditional OLAP systems have largely been pull-based systems. But an OLVM system is very different. It's a push-based system in that it eagerly maintains views on the data, and it does work when new data arrives. So on push of new data, it does the work so that when you do get around to asking for a query, that work is already done. Right? It fundamentally changes from a reactive system to a proactive system. Now, if your OLVM system is well designed, which we'll get to in a minute, you can keep the cost of this work proportional to just doing incremental changes without having to throw out all your previous work and start over computing on the whole data set. Now, Materialize is an OLVM system. In particular, Materialize is an OLVM system that speaks standard SQL, the same SQL you know and have loved for the past few decades. SQL has been very good for transaction processing. It's been great for data warehousing. And what we're going to argue here is that it also works perfectly fine for streaming data infrastructure. There's one caveat, though, which is you're going to need a system that's capable of doing this incremental processing, view maintenance, and Materialize is, of course, one such system. With that, I'm going to hand the mic over to our co-founder and chief scientist, Frank McSherry, to tell us about how Materialize actually works. Frank will talk us through how we actually get push-based incremental view maintenance for complex SQL queries and what kind of stream processing work actually gets done under the hood of such a system. And with that, to you, Frank.
Well, thank you very much, Arjun. Appreciate that. So my goal for the next few minutes is to talk you through Materialize and give you a sense for the look and feel of what it does and how it behaves, and a little bit of what's the magic behind the scenes. We'll do that, and then we'll pivot a little bit to talking through how some relatively simple SQL idioms turn into pretty powerful bits of streaming infrastructure. So let's just start with Materialize. What is Materialize? One way to think about it is it's SQL, standard SQL, on streams of data that change, event streams that are just sort of append-only streams, that sort of thing. What is it really, though? Okay, one way to think about it from this picture is that in some sense, it's a SQL 92 wrapper. So SQL 92 is a fairly well specified. It's an ANSI SQL. It's got some pretty exciting stuff in it. It's joins and subqueries and all sorts of fairly vanilla SQL features. This is a wrapper that presents as SQL 92 for people who prefer to use SQL 92. That wraps up some cool bits of infrastructure that I'm going to name check, but not really dive into detail on. So there are these systems, Differential, Dataflow, and Timely Dataflow, that are respectively a language for doing low latency incremental computation. So computation that when you change the inputs, the outputs incrementally update, doing work only proportional to the changes that have gone on. Pretty cool, pretty powerful. You might imagine how this relates to what we're about to talk about. And then Timely Dataflow below that is a little bit like an operating system for streaming data parallel computation. This is how we turn on all of our little compute nodes and get everything up and running, move data around, that sort of thing. Visually, different take on this is when you express things in Materialize, you get to just type SQL. You get to say, in this case, we're doing a group by aggregation on top of a three-way join. And that's it's an interesting thing to compute. It's kind of tricky to do on streaming data because as the inputs 1, 2, and 3 continually change, someone at least has to constantly make sure that they're all consistent, that we're showing exactly the matches that occur and no others. The aggregation that then happens on the top also needs to be consistent. We never want to show a sum and a max that disagree, for example. You can write the same thing at each of the layers below. So in Differential Dataflow, you could write a Rust program, it turns out, that computes the same thing. That's great, but people don't want to write Rust programs. Many of the people doing data analysis have other skills, and those skills map down to SQL, and so they'd much prefer that. And similarly with Timely Dataflow, even lower down, you could build manually a Dataflow graph, but you really wish you didn't have to, right? This is starting to be quite tedious, a bit like writing an assembly or something like that. And you'd really rather have the computer handle all that stuff for you. You look for it to get written eventually in the Dataflow representation because that'll be performant. But you, the data analyst, don't want to have to do this. So I have a slide or two that I'm just going to throw up, not because I want to chat about them at all. They're about timely data flow first, and then differential data flow. And the goal is just to let people pause this, the stream at this point if they want to check out what's going on here. Feel more than welcome to grab us afterwards. You can dive pretty deep on how these things actually work, but the moral really is that they work roughly as you might expect. And how they do that is indeed a pretty exciting story from my point of view. But we're going to skip it here just in the interest of trying to stay on message about SQL and streaming data infrastructure. So with that in mind, let's just walk through a little bit of a look and feel of using Materialize. What's the life cycle of data in Materialize? Now, in a standard SQL database, you might create a table, put some records into it, run some queries, maybe drop the table at the end to clean it up. That's super interesting. Streaming data is going to be a little different, and so I just want to talk through each of those bits to set the context for building infrastructure with SQL. Now, what Materialize does is it maintains SQL views, so queries that you've written in SQL, maintains those views on streams of data that change. Maybe data just get added into an underlying collection. Maybe you add and remove things. For example, you might be tracking the contents of some other relational collection that you have. SQL 92, as I said, even the hard stuff. So there's definitely hard stuff out there. The correlated subqueries and all sorts of crazy outer joins. These are things that are subtle and a little tricky to get right, but we've been really careful that it's important to get them right if we want to really enable and open the doors for people who are familiar with SQL and expect it to work correctly. And I've written here over on the left some example things that you can do in Materialize. I'm just going to walk through some examples that I've actually, this is the literal code that I'm pulling out of an example that looks at the TPCH workload. This is a decision support workload that's just asking these sort of broad aggregating queries across data and just show you what things look like. So a natural first thing that you do in Materialize when you connect to it, you connect just using a standard Postgres pSQL style connection. You can create sources. Sources are essentially names of where to go and find streaming data. There's a bunch of places you can get them out of Kafka. This example here is just a local file on my machine, and that's not the most exciting case, but I did want to be faithful to an actual work end-to-end example. We'll continually pull the file, and if you add more stuff to it, more lines, we'll pull them in a stream fashion. But think of this as being Kafka or S3, Kinesis, stuff like that. And you give just enough information here for us to make sense, relational sense of what we're seeing. So in this case, indicate that each of these lines should be treated as comma separated values, name the number of columns, the delimiter, and this now tells us this is a 17 column wide thing. Each column has type text in this case, and we can now start working with it if we want. It's a bit like if you might think of it as like an empty table, or a table that actually it does have data backing it. We just haven't looked to see what that data is yet. We're going to stream it in when you actually start to use it. So a natural thing that you might do, and that you absolutely do in this data set, is to first transform the data. So we had 17 columns that were all text. Well, we should potentially parse some of these out and turn them into typed data. So many of these are integers, some are decimal, some are dates. Some of them are absolutely still just bits of text. But this is a great opportunity to give them the names that users expect to see for each of the columns, the types. It's just creating a view. Creating a view, if you're familiar in SQL, doesn't necessarily cause any work to happen. You're just describing, in the future, when I refer to a line item, what should you treat that as? And you should treat it as each of the rows that are in line item source, that source that we named, with the following transformation applied to each of the rows. So that's nice. Like this is handy. Nothing's actually happened yet in Materialize other than us announcing how we would like to work with the data in the future. So let's actually cause something to happen. So creating views is great. You may want to create indexes on these streams. So this is the index in Materialize is essentially what causes computation actually to exist. So when you create an index on a thing, that's a statement that we take quite seriously, that you would like to have random access to the contents of a particular collection indexed by some keys. And as soon as you issue such a statement, we will leap into action and run off and start streaming the data in, and ultimately, whatever the query was. In this case, the line item query isn't super complicated, but whatever data result there, we will build into an index for you and make available inside Materialize in a way that if you go and try to read data out using the primary keys, will be incredibly fast. And if you have downstream queries that need to use these indexes, maybe you're doing joins, we'll make those indexes available to them, those queries, to make things fast in the future. But this is a moment, for example, when Materialize will suddenly spin up and start reading all of your data. It'll go, in this case, read that file that I named, but otherwise go off to Kafka and start reading data in, pushing it through data flows, maintaining indexes for you. If that all seems a bit annoying, there's some shortcuts here, right? So you can, when you create a view, you can put the Materialize keyword in front of it. We will automatically build an index for you using whatever we can about the query. This happens to be query 5 from the TPCH workload, and it does some aggregation over, in this case, it's a 6-way join between many things, ultimately aggregating down by nation name. And the results are actually pretty compact. That's nice. We could actually look at this. Materials will look and see that the nation name is actually a great primary key for this. We have, because we did a group by, we know that it'll function perfectly as a primary key. We'll use that as a key for the index that we build because you just asked that we materialize it somehow. But yeah, you can see defining a 6-way join in here is pretty idiomatic for SQL. This is literally the exact same SQL that you would type into the TPCH benchmark, at least proposes you type into your SQL system. Exact same thing here. It's just we will keep all of this data up to date as each of these underlying relations change. So each of them are being drawn potentially from different Kafka streams, different files, what have you. And finally, you can look at the data. Of course, you can type select star from TPCH Q05. We'll give you interactive access to the data as fast as we can. But you can also set up syncs for the data. So here I've just described pretty briefly how you might take the data, TPCH Q05, and produce a sync, which writes it back out to Kafka. You get to name sort of the broker and the topic and potentially other authentication stuff, but you describe how you would like the data produced as output, and we will take all of the changes that occur to that query and sync them back out to a stream in a way that downstream folks can now pick the data back up and look at it and say, oh, wow, this is, in this case, I'm delighted that someone else did the 6-way join for me and distilled down all of the results. I'm just a handy little downstream application that maybe throws data up on a UI or something like that. So in this case, Materialize has potentially added a tremendous amount of value as this bump on the Kafka wire that implements some really interesting data transformation, aggregation, and ultimately depositing the results back out there for other people to look at. And with that description of it, you might start to get a sense for how this looks a bit like streaming data infrastructure. We've described with some SQL queries a process that transforms incoming streams of data, parses them out, transforms them by joining, by grouping, by aggregation, basically any of the things you can describe in SQL, and then records the results back out into the streaming infrastructure again so that other folks can pick this up. And any work that you can absorb into Materialize at this point, into the SQL system, is great. That's the stuff that you don't have to handwrite in your streaming infrastructure. So let's just talk through a few examples of some things that you can do that really just, in my opinion, simple idiomatic SQL, but when you name what that thing is in modern data infrastructure, you get an existing name. You're like, wow, maybe I don't necessarily need that thing anymore. So all of these examples, I'm just going to write vanilla SQL, and the only difference is going to be where you might have previously thought you'd write this query against static data. We're going to present it instead as, what if the data is changing? Like, what if you had a system that as the data changes, it continually updates the outputs for you? So let's take a simple example here. You can see over on the right, we have a view that we create that selects items in hours and the maximum bid for each item in hour. That's a thing. as offers, which I'm not sure how that's populated, it's some stream that you happen to have. As data are added to that, Materialize will continually maintain the aggregations tracking items, hours, and max bids for all items and hours that you've fed things to it. Yeah, and maintain these in an indexed compact representation. There's no requirement, for example, that you take all of offers, which might be enormous, and first put it in a data warehouse. There, repeatedly hit it with some queries and write the results back out. No, you don't need any of that. Right. Materialize itself is totally comfortable reading in offers, which might be enormous, maintaining the relatively compact maximum bids for each item for each hour. Right. Of course, there may be many bids for each item in an hour. We're just going to maintain the max. And yeah, so the computation, bits of computation that you might previously have really sort of worried about, what is the pipeline to actually get this result back out? You can actually write directly against the stream in this case. Let's look at another example. So if you're familiar, data infrastructure connects a lot of different components based on their functionality. So you have streams of data, maybe something like Kafka, that move records around. You have microservices that perform computation on these things, maybe right back to Kafka. You have caches that pick data out of Kafka and present it for others to read. And in many cases, consistency is a continual pain amongst all these things. You might have stale data in your caches, for example, that you know isn't the right answer yet, but the microservice hasn't yet put the data out into Kafka, or Kafka is holding up the data for some reason. You might have multiple caches that are not consistent with each other, and it's just all quite a bit of a headache when you're trying to do something serious like authenticate a user, right? Or show the user the contents of their shopping cart. Now, this is a total non-problem in SQL. Right? You have the ability to define the bits of computation that you want to do, the microservices, and then the indexes that you build. Right? When we created an index, in this case we created an index on value, but we've seen indexes before. This tells the system, how do I want this data to be randomly accessible? Make it super fast to get the data out. So you can describe these things, and then any SQL system is going to give you consistency guarantees. Materialize in particular gives you very strong sequential consistency. And the consistency problems essentially vanish. You're no longer hand wiring together all of these bits of your system and sort of crossing your fingers and hoping that the right answers get to the right places eventually. But you get the same behavior out, streams, computation, caches, in a system that has a broad enough vision to actually maintain consistency for you. So if you asked for the results of value and also potentially that TBCH query before, you'll only ever get consistent results out the other end. You won't have to figure out, oh, maybe there's still data, flush something, wait 5 minutes, any of this nonsense. Right. If you're using streaming infrastructure, you might be familiar with the fact that oftentimes streams of data really try to focus on the most recent events. And there's a few reasons for this. Recent events are usually pretty exciting, but also if there's a long history going back in time, you got to sort of forget that at some point, otherwise your system may fall over. Now, a standard approach if you're using standard stream processors is to describe windows over your data. So to say, hour by hour, I want you to compute a thing and only show me the most recent hour and throw away any old hours. Essentially, narrowing your query down to various time slices of data on which it will react. And that can work. Like it depends what you're trying to do. There are many cases, of course, where that doesn't work. Your customer data, for example, is not windowed, right? Your customers have existed for more than an hour and will hopefully continue to exist for more than an hour. And there's another example. It's just shown over here on the right-hand side, where you might get a bunch of bids. We've been talking about bids before, but a bunch of bids that come with an item and a bid, and maybe we only want to keep the bids that haven't expired yet. Maybe they come with an expiration, and that's really hard to do in a window in a stream processor. If you've ever had to do these things before, if you've not had to do them before, trust me, it's really hard to express this. But it's super easy to express in SQL. Right? You just put something in the where clause. The where clause tells us which records we want to narrow our view down to. And if we just say that we only want to keep those records where now is less than the expiration time, it's interesting, right? You could certainly comfortably type this into SQL, and it'll show you only those records it'll grab the time now and show you only those records that haven't expired yet. But when you feed a query like this to something like Materialize, we sort of pretty, I suppose, cleverly look at it and say, we can't actually evaluate now every millisecond over and over again and reevaluate this. That would be exhausting. So instead what we do is we say, well, this tells us exactly when a record will vanish from this collection. Right? It tells us, not yet, but at O.expires, each record will expire from the collection, will vanish. And the stream processor, the underlying stream processor, can be set up to say, great, I won't do anything until that happens. Let me put it in a queue and I'll react to that future moment. And by just expressing this query with the where clause in it, you've now described a view that you will maintain over time that will automatically clean up bids that have expired, for example. Or, if you want to put +1 hour in there, you can make hour-wide windows and various things like that. But all of this is very, I would say, very straightforward where clause statements rather than new syntax about windows and sliding or skipping or stumbling windows or however you like. All right, the last example I have is a bit magical, and I don't think I'm going to nail the description of this, but I'd like to at least wet your whistle here. So what a lot of folks do with streaming data is they're trying to build applications. They're trying to build a little bit of logic that takes input requests, essentially, little statements saying like, here's some parameter username and a query term and list of how many results you want to see, and feed that into a bit of computation that comes out the other end and says, I thought really hard about all my data, and these are the answers for you. And you can clearly write some imperative code to do that. You might be a little hesitant to say that that looks like SQL, but in fact, there's a really cool way to express all of this in SQL using what are called lateral joins. And a lateral join, you can sort of see it in the example over here. The highlighted region is sort of part of the lateral join. What a lateral join lets you do is say, for a collection, in this case it's called queries, execute some other subquery where the subquery is allowed to reference the columns in queries. Essentially what it says is for every entry in queries, rerun a new subquery where you've bound some quantities, and you put your query arguments in here, for example. This is getting the top 3 cities by state, for example. And in standard SQL, I don't know, it's not always so common to see these things. Lateral joins are cool, but they do something really amazing in streaming systems when the queries collection can change. Right, so if I add a new entry into queries, I'm from Vermont, so let's say we add state of Vermont in there. The correct answer for the result will change. It'll change in a way that now it needs to include the top 3 cities in Vermont by population. And so the result of the maintained view, when I introduce a thing that says, please add Vermont, will now be a new 3 new cities in the output that says, Vermont 1, Vermont 2, Vermont 3. Just as if I had written an application that would have gone off and figured these things out by executing a query. And that's super cool from my point of view. If you're familiar with prepared statements in something like SQL, this is where you take that highlighted region and say, I want to issue this query over and over again. This is a bit like prepared statements on steroids. You can stream in arbitrary changes. We'll do the query execution using exactly the same in-memory assets, ready to go at any moment. And it's really cool. It's a thing, again, it doesn't make a lot of sense to write your queries this way against static data. But when you say, what does this do against stream data? It gives a really interesting new behavior. Essentially, as if we had a little database in there that we could repeatedly call this query on with different parameter bindings over time. All right, we're going to wind down a bit now. I just want to have a slide here about some challenges. Why isn't this easy? Like, why doesn't every vendor out there have one of these sorts of systems? And there are some challenges. I just want to call them out so that you don't think this is too magical. All of these queries need to be data flow. Things, for example, those lateral joins, a lot of databases would implement them just as sort of shelling out to the query engine, say, well, just issue a new query. We can't do that. And if you want to have a fully reactive system, you can't do that. Right? If the actual population data changes at any point in time, you need to figure out, oh, geez, well, which queries did I issue that I have to correct now? And it's complicated. Control flow interruption is challenging. So if you have errors, you don't want to take down your whole computation. You don't want to just crash everything and say, oops, there was an error. So you have to be fairly careful threading error handling through all this so that if you produce data that maybe introduces an error, like a division by 0, and then later retract it, great. We'll retract the error again and return the system back to the state in which you were actually seeing correct answers. And finally, optimization is just fundamentally different. Rather than trying to get in and out as quickly as possible, which is sort of the standard approach to query processing, minimize the execution time of the query, we're much more interested in the ongoing costs of queries. So the memory footprint over time, for example, is something we really try to minimize because that's what prevents people from asking as many queries as they want. The throughput of these data flows is important because that's the ongoing CPU burden of the queries. So it's just fundamentally different things that mean that it's not trivial for an existing database to just pivot and suddenly start providing this different behavior, different functionality. All right, to wrap up, we've claimed, hopefully given you a bunch of evidence, that standard SQL is expressive enough for streaming data infrastructure tasks, with the caveat, of course, that you need to have infrastructure that actually supports that. Materialize is such a thing. We're pointed at SQL 92 compatibility, really trying to play nice with Postgres and PGWire so that if you've got tooling that maps down to Postgres, you should be able, in the fullness of time, to just point it right at Materialize and it'll work. It's got some of the really nice big data properties, so it's scalable from one thread. So you can run this on your laptop if you want. You don't need a cluster of various Apache services. Run this on your laptop single-threaded, all the way up to multiple cores, multiple machines. You get the scaling and latency properties that you'd expect out of solid big data systems. It's consistency preserving in the sense that if your data provide information about transaction boundaries in them, we'll respect that. And if they don't provide that sort of information, we'll make stuff up and then we'll respect whatever we made up. You can read a lot more. So if you head to materialize.com, there's a whole bunch of stuff that you can get, downloads, docs, demos, all sorts of great information about what Materialize is, how it works, stories, blog posts about really cool things you can do. The code is also available. You can go to Materialize Inc. on GitHub, and we do all of our work in the open. And the underlying compute infrastructure, Timely Dataflow, is all open source. You can also go and check that out independently. And if you'd like to get in touch with either of us, Arjun or myself, Frank, you should feel more than welcome to. Thanks very much.
Fantastic. All right, we're coming back here. All right, that was great. So we do have a few minutes to go over questions, and then we'll finish at the 40-minute mark. I do see a few questions here, so let's jump in. So Ian says, what's the reason for wrapping SQL 92 and not something a bit more modern? For instance, window functions are very powerful and they were introduced in SQL 2003.
So I can take that. This is Frank. So you're absolutely right. Window functions are super exciting. We'd love to add them. We probably will in the near future. They're a bit more complicated to maintain incrementally is the main pain point as compared to things like joins and subqueries. So we started with the things we knew we could do well, and we're going to be building up essentially more and more SQL functions functionality as we go.
Perfect. Rebecca asked, what are some of the use cases? And I assume we're talking about the real-time processing, but if that's the case, please clarify.
Yeah, I'm happy to take that. I'm Arjun. The sort of short answer is, anything that you currently do in batch analytics today that would benefit from being done, that would be benefit from being live, is a good candidate. A good example of this is dashboards that are refreshed once a day, that are used by data analysts. Even less what you might think of as less analytics focused, like customer success and customer service dashboards, where oftentimes there's a live human on the line who encounters a problem with their system, and there's an agent that's looking at a data feed or some view of data that would really benefit from having up-to-date information. But broadly speaking, the candidate said it's not just it's not just extremely low latency use cases. Of course, that is one use case. It's anything batch that today updates once a day or once every few days that would just benefit from being up to date.
Great. Okay, let's keep moving on here. Mike asked, do you see a use in IoT scenarios where we need real-time go, no-go decisions?
Yes, absolutely. IoT is one of the use cases where users are using Materialize. In particular, what I would call out about the go no go style analytic decisions that you called out, they really benefit from a focus on consistency, right? So consistent systems that when they give you an answer, you know that answer is correct as of the input data is very, very valuable when you're going to make take some action as a result of that, as opposed to eventually consistent systems where you may need to wait a minute to see if the answer is stable or shakes out to be something else. Those eventually consistent systems, which traditionally have been more prevalent in streaming or in NoSQL worlds, are not very useful for this actioning, whereas a fully consistent system is a lot better for that sort of situation.
Let's go back to another question here from Ian. What do you suggest for handling the duplicate code bases that come from using a SQL-based streaming? Do you deal with duplicate code bases, streaming and batch? Apache Beam, as a counterexample, has the same API for both.
Yeah, so I think it's actually a great example. By using SQL and really by sticking to actual SQL, not sort of SQL with some asterisks or caveats. We've got a lot of people who just literally take their SQL that they've been using on, let's say, their batch workload, just put it into Materialize, and they get the same answer, and they're delighted. And that's really helpful in contrast with two systems, let's say even two SQL systems that use slightly different flavors of SQL, where you got to go figure out, how are the nulls different in this case versus that case, or they don't support certain bits of functionality. So I think it's actually stepping in the right direction to focus people's attention on SQL, because there are already so many large volumes of code bases in SQL, and just supporting the same code without needing a new API for, although Boom has the same one in both cases, it's still new. You got to port all of your logic to that.
Great. Let's do one final question here. What do you see the future of real-time processing systems to be?
Materialize, obviously.
I'm happy to take that one. I generally think real-time systems are today very, very difficult to use. So some of the things, for instance, Ian's question around sort of duplicate code bases is a very salient problem that people have when deploying, or were deploying real-time systems in the past decade. You basically have parallel infrastructure, one for batch that has a lot of benefits, which deals well with data integration issues, it uses, a tremendous amount of research has gone into optimizing SQL and making it easy for analysts to write, things like that. And then you have this parallel ecosystem of sort of Kafka-based microservices that just don't have the same level of tooling, mainly because the tooling is itself an ecosystem of SQL, like there's, dozens of companies that will help you at each stage of the SQL batch pipeline, and that same ecosystem does not exist in streaming. And I think the future of streaming is really SQL, which is to plug into that same ecosystem that worked for batch. So streaming and real time will look a lot more, sort of merge into the batch ecosystem. I think the thing that we really are driving towards at Materialize is really want to support the exact same SQL that people have known and loved for 3 decades, such that moving from once a day batch to second by second, millisecond by millisecond streaming is really more of a flip of a switch. You're flipping out the underlying execution engine, but really the same SQL, the same business logic that you've built up for years and years just sort of works without too much more data engineering.
Great. I think we'll finish on that note. Any final comments from either of you?
I was just gonna call out. Sorry, I typed this, but I'll be available in the networking room after folks have other questions they want to get into. Super appreciate the opportunity to present to all of you all, though.
Same here. Thanks very much.
Perfect. Thank you. Thank you, everyone. So we will have one more session in this track, which will start in about 20 minutes. So be sure to check that out. Make sure to also check out the networking room where both Frank and Arjun will be there. You can continue the conversation there. And finally, one final thank you to both of you.